Morning, everyone. Well, first, I'd love to thank you all for making the effort to be here with us today. For the following 50 minutes, I'm going to present my current research work on direct current triboelectricities from sliding Metal-Monolayer-Semiconductor contacts, where the AFM is mainly utilized. So just saying a few words about myself. I come from a municipality called Chongqing in southwest of China. I got my bachelor degree in Shanghai and master degree in Australia, and currently a PhD student here in Curtin University in Australia. Now let me start my talk today now. So with the development of electronic technologies, the growing number of microelectronic devices have been manufactured to facilitate our life, such as all those wearable devices, the IoT technologies, where is the functions of sensing, monitoring, communication, and even some implantable life-critical devices, such as pacemaker. But there is an apparent defect that is the power source of those devices. Practically battery at this stage has the problem of limited lifespan, and it's a non-regenerative sources, making it inconvenient to recharge and replace, especially in inaccessible locations, such as inside the human body. Well, the nature moment provides us a broad range of mechanical energy sources, ranging from the contraction of our blood vessel to the vibrational energy of an acoustic wave, but most of them are hard to be harnessed using the traditional technology due to its low frequency. Thus, a new power technology, which can be used as a continuous direct current power source like battery, but not necessarily increase the size of devices, is ideally required. So in other words, we're expecting a technology which can generate direct current without any external rectification circuit. So one of such technologies is triboelectric nanogenerators, which in abbreviation is TENGs. It's a device that could convert mechanical vibrations, such as tidal waves, human motion, and even falling rain droplets into electricity. So here comes a new concept called triboelectricity. Tribo comes from Greek, meaning friction. So in a simple way, I would call it a friction-induced electricity. So most recently developed TENGs, as shown in the figures, they have two kind of working modes, and they basically generate alternating current by sliding one material against another, or via the cycles of contact and separations. Here, we mainly focus on the direct current electricity in the miniaturized sliding contacts between metal and semiconductor. Here, we select silicon, considering its rectification characteristics and relatively low cost. Then we'll see if we can find a method to improve the direct current output while keeping the frictional wear and damage of devices at a relatively low level. So as I was saying, the great majority of published TENG's design is alternate current. But while as noted, all the electronic devices are generally powered by direct current. That's why we aim to develop a DC TENG. One of those very promising form of DC TENGs is the zero bias sliding semiconductor metal diode, or I would say sliding Schottky diode, as shown in the left pic. So luckily, the conductive AFM works basically the same way as the schematic of the sliding Schottky diode, as long as we use the conductive metal tip. Here we chose the platinum tip. Hence, the research and collaboration between tribo current output and friction becomes possible. Also, thanks to the recently developed self-assembly surface chemistry, we can electrically stabilize the oxide-free silicon surface under ambient, oxygen-rich conditions. Therefore, we attempt 4 different organic self-assembling monolayers, which is 1,8-nonadiene, 109, and 8-991-ol, and 109-ol, just to say if the different terminal functional group will have any influence on the triboelectricity performance. So before I present my results, I would have a brief introduction about the 2 mechanisms coexisting in the energy dissipation process in friction. One is the phonon mode. So in microscale, the thermal vibration of atoms in contact interface excites phonons to release the energy via sound. Another mechanism is the generation of electron-hole pairs during sliding contacts, which is the main focus of our research. So considering the material we used, metal and silicon, the dynamic metal-semiconductor junction, also as Schottky diode, will form in the contact surface. So similar to photovoltaic effect, the proposed triboelectric effect generates electron-hole pairs in the interfaces via friction excitation. But the intrinsic connection between the friction and current, as well as the potential inducing factors, remaining unclear at this stage, which naturally becomes our purpose and aims of our research. At first, we'd love to determine the relationship between the zero bias current and stick slip friction as its main reason of wear and damage of components. Now, by using AFM, here we can obtain the height images and the current maps without external bias on the 109 modified silicon 111 surfaces. So as we can see from the image, it clearly displays the terrace of silicon 111 facet with negligible oxide detected. And the direct current signal is at the same direction of leakage current, which in our case, from the silicon to the metal tip. On the right side, we extract the friction and current profile in the marked line A to B. Here we'll attempt to confirm if the zero bias current is related to the energy accumulation and release process during stick slip event. The correlation between current and stick slip motion is quite ambiguous, as each stick event, marked in blue area over here, doesn't correspond uniquely to the increase or decrease of the current, which has been marked in green and red. Hence, we rule out the simplex dependence of current microscale stick slip friction, hence making it possible to harness triboelectricity without sacrificing the life of sliding friction parts. Next, we continue to conduct conductive AFM tests on silicon 111 surfaces with different organic monolayer terminating with different functional groups. Here we present the current maps and the height images on modified silicon 111 surfaces. The alkyl monolayer, which is figure A over here, we use 80910. It possesses the highest current density among all, as we can see from the scale bar. It goes to nanoamp scale, while all the other three monolayers are in the scale of picoamps. So and also it's easy to see that the current signal has a rapid rise as the step of the 111 terraces. And the phenomenon is even more evident for monolayer with high direct current output, such as a 090. Here, referring to the stereographic projection of the silicon 111 wafer, we speculate that the reason is because the exposure of the more conductive silicon 211 surface at the step of the silicon 111 terraces. Hence, we again conducted the following conductive AFM current mapping on monolayer modified silicon 211 surfaces. Although 211-oriented silicon doesn't show clear terraces as silicon 111, but there's still no obvious oxide is detected. On a silicon 211 surface coated with organic monolayers, the overall current surpasses that of 111-oriented silicon. And the most exciting things is that the maximum current density on alkyl modified silicon 211 surfaces reaches over 3 times 10 to the power of 7 ampere per square meters, which is even 1 order of magnitude higher than similar zero bias Schottky diode recently published in Nature. And to further validate the results, we performed the contact area estimation to eliminate the influence of different contact area due to the adhesion force of different organic monolayers. So by using the DEMT models and the force distance spectroscopy function on AFM, it makes it possible for us to express the zero bias current signal in terms of current density to have an effective comparison. Besides, we conduct current voltage measurement at the equivalent triple voltage, which is negative 0.4 volts, at which the zero bias current is completely offset during sliding process. The trend in current density for different organic monolayers doesn't match with the sliding zero bias current maps shown before. It indicates that the dynamic sliding Schottky diode has its own energy dissipation mechanisms, which is quite different from the static Schottky diode. This is crucial for the further study of triboelectric theory, and it rules out another possible factor that could limit its potential performance. And in the future, we're going to keep probing the possible influencing factors of triboelectricity and possibly at the same time test its durability with the Park AFM. With a new function of photocurrent map, we would like to see if it has the same kind of surface recombination things, will it influence the triboelectricity generation output. And at last, thank you all for listening. And here I would especially show my gratitude to Park System Corporation for inviting me to do the presentation here today and share my experience with Park AFM. And thanks for the assistance from support from my supervisor, Professor Semeni, Curtin University, and the Australian Research Council. Thank you, guys.